Okay, so we ended the last section kind of introducing these other indeterminate forms, but we didn't really talk about them. So when you see this, 0 times infinity, infinity minus infinity, 0 to the power of 0, infinity to the power of 0, 1 to the power of infinity, all of these just as expressions are undefined. But that's not what they're not meant to be thought of as like arithmetic. These are forms representing limits. So for example, 0 times infinity is an indeterminate form where you have a function like f of x times g of x, limit as x approaches a, where one of the functions will go to 0 as x goes to a, and the other one is going to infinity or negative infinity as x is approaching a. Basically what's happening is you're getting a product of functions where one is getting really, really small in the sense of going towards 0, and one is getting very, very large in absolute value, meaning far from 0. And so the product of these things does this weird balancing act. A small number times a big number can be anything in between. So this form is describing a situation like that, where one of these goes towards 0 while the other one goes towards plus or minus infinity. These guys, these three here, are all of the form, f of x to the power of some other function g of x. And we're looking at a limit where x is approaching a. And these forms are describing what's happening to f and g as x approaches a. So for example, the infinity to the power of 0 case, the inside function as x approaches a would be going to infinity, and the exponent would be going to 0. And again, we get this balancing act. The base of this exponential is getting really, really big, but the exponent itself is getting really small towards 0. So there's a balancing act, and that may come out to something other than infinity or 1. It might come out to anything. And then similar here, infinity minus infinity. You have something of the form f of x minus g of x, and we're looking at the limit as x approaches a. And if both of these go towards positive infinity, you're getting a number that's really, really big here, but then you're subtracting another really, really big number here. And so the subtraction might create that balancing act. All of these cases are indeterminate forms, and we can use L'Hopital's rule in many of the cases where we have one of these, but not directly. And what I mean by that is that L'Hopital's rule specifically only applied to indeterminate forms of the type 0 over 0 or infinity over infinity. So in order to make L'Hopital's rule work in these kinds of cases, we have to algebraically manipulate those limits until we get one of those other two forms. So to give you an example, here we have the limit as x approaches pi over 2 from the left. So this is a one-sided limit, and you're going to see several of these in this section. I don't know why I put a -1 there. From the left, of cosine of x secant of 5x. This is an indeterminate form because if you look as x approaches pi over 2 from the left, cosine is going towards 0. Secant 5x is undefined here, but if you were to plug in pi over 2 to this is going towards infinity. You would see that if you just plugged it in, or if you looked at the secant function, like a graph of the secant function, this is going towards infinity. So this is of the type 0 times infinity. And that's an issue because, again, we don't know what that is. So what I'm going to do is rewrite this as the limit as x goes to pi over 2 from the left of cosine of x over cosine of 5x, because secant of 5x is 1 over cosine of 5x, and then multiplying them would give me this. So using a little bit of my trig identity knowledge, I can put this in a form that's more useful. Now notice this is of the form 0 over 0, which you can verify by direct substitution. Now I can use L'Hopital's rule. I put it in a form that's usable. Okay, so let's try that. The limit as x approaches pi over 2 from the left. I take the derivative of my numerator and denominator separately. This gives me negative sine of x over negative 5 sine of 5x. Okay, if I plug pi over 2 directly into this, I get negative 1. If I plug pi over 2 directly into this, it becomes 5 pi over 2, which is coterminal to pi over 2, and so it's the same thing as sine of pi over 2. And I get a 1 times negative 5, or just negative 5, giving me an answer of 1/5. Okay, not too bad. L'Hopital's rule was only needed once in that example. Okay, here's another case, and this time we're looking at the limit as x approaches 0 from the right of 1 over x minus 1 over inverse tangent of x. Now, both x and the inverse tangent of x, if I try to substitute 0 in directly into both of those, is either infinity or it's equal to infinity. So 1 over these, both of these, I'm sorry, let me back that up. Plugging a 0 into x and plugging a 0 into inverse tangent of x is equal to 0. So it's like 1 over 0 minus 1 over 0. Those are undefined. Thinking of it in terms of limits, the limit as x approaches 0 from the positive side of each one of these is infinity. So I'm looking at an infinity minus infinity type of indeterminate form. Okay, direct substitution doesn't work here. But if I can algebraically manipulate this to put it into a more usable form, I might be able to apply L'Hopital's rule. So I'm going to write this: the limit as x approaches 0 from the right of 1 over x minus 1 over inverse tangent of x. I can get a common denominator here and combine these into one rational expression. This is equal to the limit as x approaches 0 from the positive side of the inverse tangent of x minus x over x times the inverse tangent of x. I'm skipping the algebraic steps that would be needed to show, me getting a common denominator and combining these, because there is enough work to do in this problem. Now, are we looking at one of those indeterminate forms that allows me to use L'Hopital's rule? Well, again, plugging 0 in directly gives me 0 minus 0 over 0 times 0. This is a 0 over 0 indeterminate form. That allows me to use L'Hopital's rule. So I'm going to do that. I'm going to take the derivative of the numerator and denominator separately. So this is the same thing as the limit as x approaches 0 from the right. The derivative of the inverse tangent function is 1 over x squared plus 1. And then minus x becomes minus 1. I need the product rule down here, so this becomes inverse tangent of x plus x times the derivative of the inverse tangent of x, which is x over x squared plus 1. Now, this thing is kind of messy looking, so I'm going to try and simplify it a bit by multiplying that denominator out. I'm going to multiply by x squared plus 1 over x squared plus 1. Okay, this becomes the limit as x approaches 0 from the positive side. Multiplying the x squared plus 1 is going to cancel that denominator, give me a 1, minus 1 times this, so minus x squared plus 1, over, then down here, I'm going to have x squared plus 1 times the inverse tangent of x. And then I get a cancellation happening here and here, so that becomes plus x. Okay? I can simplify this a little bit more. 1 minus that 1 is going to be a 0. And so just with a little bit more simplification, I can write negative x squared up on top. X squared plus 1, inverse tangent of x plus x. Now, will direct substitution work? Unfortunately, no, because once again, you can verify I get 0 over 0. So that means I have to use L'Hopital's rule a second time. Scrolling up a little bit. Using L'Hopital's rule again, this becomes negative 2x over. Now, I need the product rule here. So if I take the derivative of this first thing, that's 2x times the inverse tangent of x. Then x squared plus 1, think about this for a second. What is the derivative of the inverse tangent of x? Well, it's 1 over x squared plus 1. And that's being multiplied by x squared plus 1. That's going to come out to just 1 plus x becomes plus 1. Okay? Simplifying this down a little bit, I get 2x to inverse tangent of x plus 2. I also have a minus 2 up here. I get a bunch of 2's that can cancel out. So this becomes the limit as x approaches 0 from the positive side of negative x over, canceling that 2 gives me x inverse tangent of x. 1 plus 1 is 2. Canceling the 2 gives me a 1 right there. Okay. Is this still an indeterminate form? Well, it's actually not, because if I look at this, the limit as x approaches 0 from the positive side, I can plug 0 in, and I get 0 up on top. A 0 here plus 1. This becomes 0 over 1, which is simply 0. Okay? So I actually got a limit after that second application of L'Hopital's rule. It was a little algebraically messy, but not too bad. We've seen worse.